Alright, so using atoms as the basis for representation, so we need to determine the vibrational mode of this compound pyridine. So basically, the first thing is to identify the point group. So, and for you to identify it, let's draw the structure. So this is pyridine. We have it to be C. We have N. So we have this C, C, and N. So there's hydrogen here, hydrogen, 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 hydrogen. So this is the structure of pyridine, right? So let's identify the symmetry elements. The symmetry elements here are basically, we have the identity, because identity is what you carried out that leaves the molecule unchanged actually. So identity, we have identity there. So which proper axis of rotation do we have? Let's check for C2. So let's say we have this point here. Yeah, this is C2. I will carry out C2. So if we carry out C2 operation, this structure will be, let's say we have this one to be 1, this one to be 2, 3, 4, 5, right? So when we carry out C2 operation, we're going to have the structure to be so this has flipped with this one because we simply rotated here. So this one comes here, becomes 1, this one comes here, becomes 3. So we have this one 5, 4. So we have 5 and we have 4, right? So this is C2 operation. It's still the same as this structure, right? So C2 operation is possible. So can we have C3? No, impossible. C4, no. C5, no. So how about C6? If we have C6, this one will move here. So H2 will move here, H3 will move here, H4 will move here, and N will move here. So this is definitely not going to be the same as the initial structure. So C6 is not possible. So let's now look at mirror. Can we have sigma? So can we have sigma H? That is the perpendicular mirror plane. So this is the principal axis. If we have a perpendicular mirror plane here, it's still not going to give us the same structure. This part will not be the same as this. There's N here, there's no N here. So that one is out already. So let's now look at the parallel perpendicular plane, or the parallel. So this is the principal axis. So if we have a mirror plane that cuts through here, let's say we have a mirror plane that cuts through here, right? So basically, what is here will be showing here. A part of N will be showing here, a part of N will be showing here. So this is the same as the same structure, because basically what we are seeing here, we're also seeing it here. So this sigma V is possible. So can we have another mirror plane? So let's say we cut everything this way like this. If we have it this way, so this gives us another mirror plane. So we can have sigma V prime. So these are the symmetry elements of this compound. So, and this symmetry element basically will give us C2V point group, right? So it gives us C2V point group. If you don't get how we got the point group, you may want to check the video on point group. So this gives C2V point group. So now the next thing we need to do is to calculate the character for the reducible representation. So we already know that C2V, right? So these are the elements. We have E, we have C2, we have sigma V, and we have sigma V prime. So we have this to be this, right? We have this, we have this, this. So this part is the number of atoms. So let's do it in the next slide. So we have identity, we have C2, we have sigma V prime, sigma V prime prime. So the first part is number of atoms unshifted, right? So this is basically the number of atoms that was unshifted when we perform this operation. So the next one is the contribution per atom unshifted. So per atom unshifted. So this will give us the character of the reducible representation. So we are looking for character of reducible representation. That was basically XR. That's what we are looking for here. So let's partition this. So something, looking at the structure here, this is the structure of pyridine, right? We have this N, C, C, and C. So we have hydrogen here, hydrogen, hydrogen, hydrogen. We have hydrogen, right? So this is the equilibrium. So this is the resonance. So and so C2 cuts through here, right? So that's our C2. So when you perform identity, you are basically not touching any of the atoms. So number of atoms unshifted when we perform identity is all the atoms. So let's count all the atoms. We have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 atoms here. So when we perform C2, number of atoms unshifted are, we have this, we have this, and we have this. These are the number of atoms unshifted, that's 3. So when we perform the first mirror plane, so this mirror plane that cuts through here, so it's cutting through the hydrogen here, the carbon here, and the nitrogen here. So the number of atoms unshifted here is 3. So when we now perform the second mirror plane, it's cutting through all of the atoms, right? So it's cutting through all of the atoms. So basically, it's going to be 11, right? So this one is constant. The contribution of identity is always positive 3. The contribution of C is always negative 1. The contribution of mirror is always positive 1. So this one is positive 1. The last one is identity, but we don't have identity as element here, so we are not including it. So identity is negative 3. So let's get the character of the reducible representation. So this one to be 33, this one is minus 3, this one is positive 3, and this one is positive 11. So basically the character of E is 33. The character of C2 is minus 3. The character of sigma V is okay, let's say sigma V prime is plus 3, and the character of sigma V prime is positive 11. So the next thing we need to do is this. So we already said that the character of identity is 33. That of C2 is minus 3. That of sigma V is plus 3, and that of sigma V prime is 11, right? So the next thing we need to do is to get the value. We want to get the value of the determine the value of the irreducible representation, right? So we're going to use this value, this equation, this formula rather. So A1, this is A1, we replace it for A2, we use the same. Replace it for B1, we use the same, and replace it for B2, we use the same. So H is the summation of the coefficients of the symmetry element. So basically the coefficient here is 1, coefficient here is 1, 1, and 1. So the summation of all the coefficients is 4. So the order is basically 4 here. So when looking at this equation here, so this one is telling us that NR is the operation coefficient, right? Operation coefficient. So looking at this, we basically have that the coefficient here is 1 for E. The coefficient here is 1 here, is 1 here. So N is basically 1 for all of them. So now for the irreducible representation, these are the values that we have here on the table. But for the reducible representation, these are the values that we got here. So now let's start with A1. So for A1, we simply have 1 over 4. Then we have summation of N1 for this E. We have it to be 1 times the irreducible representation. So this is the value of the irreducible representation to be 1, and the value of the reducible representation to be E. This is we are dealing with E here. So this is 33, right? So what you need to do is simply put it this way. Put it E C2 sigma V and sigma V prime, right? So let's put it partition. So this one becomes we have it to be this yeah, plus, so it's going to be plus. So the C2, the coefficient of C2 is what is the coefficient of C2 is 1. So this is plus, we're adding it to get everything on the row. 1 times, so the irreducible representation is 1 times the reducible representation is 3. So we have this to be 3. So the next one is what is 1, the coefficient is 1 times 1 times 3. So recall that this C2 is negative 3. Please put it there, negative 3. So the last one is what? 1 times 1, N is 1, the irreducible is 1, and this is 11. So that will be 1 times 1 times 1. So everything here becomes 33 minus 3, 33 minus 3 plus 3 plus 1. Sorry, this is 11 rather. This is, we have 11 here. This was 11. So this is plus 11. So we have 44 instead. 44. So this one gives 11. One thing you need to know, anytime you have a fraction, just know that you've done the wrong thing. Anytime you have a fraction, you can never have a fraction. Once you have a fraction, you've done the wrong thing. So we have 11A1. So let's look at A2. So A2 is going to be 1 over 4. So E for A2, we have it to be 1 times 1, right? So 1 times 1 times the reducible representation is 33. So this one is also 1 times 1, right? 1 times 1 times minus 3. So we have minus 3 times minus 3 rather. So the next one is 1 times minus 1 times positive 3. That will be 1 times minus 1 times 3. And the last one will be 1 times minus 1 times 11. So that 1 times minus 1 times 11. So this one becomes 33. This one is negative here. So this should be negative. Minus 3, minus 3, minus 11. So everything here should give 16 over 4. So we have this one to be 4. This one was minus 3. Remember, we take note of that one. So here is minus 3. So let's look at B2. B2 is going to be 1 over 4. So we have B1 rather. So B1, 1 times 1 times 1 times 33. This one is 1 times minus 1 times minus 3. That will be 1 times minus 1 times minus 3. So this one will be 1 times 1 times 3. 1 times 1 times 3. And the last one will be 1 times minus 1 times 11. 1 times minus 1 times 11. So everything will give will be equals to 33. This one becomes plus, so plus 3 plus 3 minus 11 over 4. So we have this one becomes so this one becomes 28 over 4. That was 482 rather. So our B1 is 28 over 4. That's basically 7. So let's look at our B2. So B2 will be 1 over 4. So we have this one to be 1 times 1 times 33. That will be 1 times 1 times 33 plus 1 times minus 1 times minus 3. That will be 1 times minus 1 times minus 3. So plus 1 times minus 1 so 1 times minus 1 times 3. So this is plus 1 times minus 1 times 3. And the last one we have it to be 1 times 1 times 11. That will be 1 times 1 times 11. So we have this to be 1 equals to 1 over 4, 33 plus 3 minus 3 plus 11. So this is brackets. So we have it to be 44 over 4 equals to 11. So this is 11B2. So just take note that anytime you have a decimal as your division, just know you've done the wrong stuff. Now, so the value of the reducible representation, so the value of we have it to be 11A1 plus this one is 4A2. This one is 7B1. So we have 7B1 plus the last one, which is 11B2. So this is the total number of degree of freedom. Recall that we say that degree of freedom, each atom in a molecule has 3n degree of freedom. So let's say this compound has, this is pyridine, it has 11 atoms. That should be 3 times 11. That's 33 degrees of freedom, right? Degrees of freedom. So when we add 11 plus 4 plus 7 plus this, we have 33. So this confirms that we've done the right stuff. So there are 33 degrees of freedom. Now we need to assign which one is translational degree of freedom, which one is rotational, and which one is vibrational. So looking at this, since pyridine, when the compound is symmetrical, the vibrational degree of freedom will be 3n minus 5. But when it is not symmetrical, it is 3n minus 6. So pyridine is not symmetrical, so we are using this. So the degree of freedom will be is going to be V will be 33 minus 6, and that will give us 27 degrees of freedom. Now let's identify that. All right, for us to identify that, let's look at this. So every one of them here, like let's look at it. So this X, those represented with X or Y or Z, they are translational. So they are translational, right? So those represented with Rx or Ry or Rz, they are rotational. So those represented with quadratic functions like xk, yk, zk, or even xy, xz, yz, or even something like sk minus ysk. So this one are now let's look at it. So here we have A1, let's write it translational. So we have translational, we have vibrational, right? So looking at it, our translational is X. So we have one A1 here, sorry, Z here. So this one is translational. So we also have another translational here, B1. We also have another translational here, B2. So vibrational, rotational rather. This is rotational. Let's write it here. So we have it to be A2. We have it to be B1. We have one here to be B2, right? So the next thing we need to do is to now get the vibrational degree of freedom. So when you remove A1 from this, you are left with 10 A1. So that's the vibrational. So this 4A2, when you remove A2 from this, you are left with 3A2. So B2, we have 2 B2 that we are removing from this. So B1 rather. So that gives us 5 B1, and the last one B2. So we have 9 B2. So these are basically the vibrational mode of in the compound. So the question now says determine which one are IR active. So determine which of the vibrational modes are IR active and Rahman active. For you to do this, you simply need to look at this. So what you need to do is this: all of them that show. So A1 basically show as quadratic function. So this is also quadratic function. This is quadratic function. This is quadratic function. So basically all of them, they are Rahman active. So when you have quadratic function in the role of that, let's say A1 here, so there's quadratic function here. So basically A1 is Rahman active. So there's quadratic function here. So A2 is Rahman active. So this one is also Rahman active. B1 is Rahman active. B2 is Rahman active. So now let's look infrared active. Infrared active. So it's just like the values of the translational. So X, this the Z here. So this one is infrared active. So there's no X, no Y, no Z here. So this one is infrared inactive. So B1 is infrared active because it has X, and B2 is infrared active because it has Y.